Today, we'll have John Hawkins, a friend and former colleague from the times in we both were working at the Omnia team at CBA, who is currently the chief scientist at Playground, a company that is in the ad tech space, who would say that you can make money from ads online. And he's going to give today like a very interesting talk that will take us from the most basic text processing models to the most advanced transformer and attention-based. What I think is a very interesting exercise because it will help us to understand the evolution and how we progressively have been evolving into more complex solutions able to tackle more advanced problems, but also will give us like this perspective of other solutions that we can apply when we are trying to solve a problem that are not necessarily based on LLMs and the most trendy and hype technologies, but that are probably equally, if not more effective than the LLMs that we are now hearing so much about. So without further ado, I will leave the stage for John. Thank you, John, for doing this.
Awesome. Thank you, Jose. Great to see you, and thank you for the introduction. So as Jose sort of described there, this talk is going to be talking about history of text processing from really simple ideas to the more complicated ideas. Actually, before I dig into it, how many people here, and I guess for those online, do a thumbs up if you're currently doing ML with text, if that's something that you currently do or have done? Seeing, cool, good portion. That's awesome. How many people are doing that using transformers? Almost the same amount by look of it. That's cool. Awesome. So what's hard with the online is I can't gauge the percentages. So I'm presuming that's not everyone. So the idea is this will be, the talk will be partially, if not wholly, revision for some of you. But my hope is that because I'm going to lay it out sort of sequentially, talking specifically about the problems that were trying to be solved as we moved from technology to technology, you might get something out of it, particularly thinking about how researchers have gone about focusing on a specific problem and designing a technique to solve that specific problem. So actually, I'll try and use that's all right. So outline, basically, I'll talk about modeling with text and what makes it difficult. And in particular, the emphasis there will be what the difficulty of using, of modeling on sequences and how that drives a lot of the work in machine learning on text. And then sort of in order, I'll talk about n-grams and TF-IDF, semantic spaces and word embeddings, then recurrent neural networks and how they deal with sequences of text, and then on to how the attention mechanism got introduced that led to self-attention. Oh, that's you, Jose, I think. And then to all good? And then self-attention, which is the kind of one of the core critical ideas in the transformer network. So text has many unusual properties. So it has all of the kind of problems that we typically get with other kinds of data for machine learning, but it has additional specific ones. The first and prominent one being its variable length. So you could be processing a single phrase or a paragraph or an entire document. So it has widely varying lengths. It can come in many potential languages, and those languages can be, some of them can be high support languages like English, where there's enormous amounts of data to work with. Some of them can be low support languages, where there's not even that much digital copies of those particular languages. There's multiple potential encodings, even for the same language. And then there's varying sources of error and confusion in that. So typos, in the way things are written, both sort of grammatically and the way words are spelled. They can be encoding problems, so it's not always, anyone who's tried to do any serious amount of web scraping knows that this is not a perfectly solved problem. And then there's transcription errors, there's slang, dialects, and deception. So instances where the people providing the text data are deliberately changing it in a way that makes it difficult for ML models to deal with. So many problems, but at the core of it is this variable length problem. So, and the reason this is a problem for machine learning is because machine learning typically requires fixed length input vectors. So any time that we're able to deal with text inside a machine learning algorithm, we've got some way of dealing with this problem. So before the kind of neural network revolution of the last 20 odd years, there was if people were using, for example, support vector machines, you would do a kernel trick. The trick would be the kernel would be the thing that could compare variable length inputs so that the rest of the machine learning could sort of move ahead as it usually would, not without being aware of the fact that the inputs had this variable length. And so everything that deals with text and machine learning always has some way of coping with the fact that you've got variable length inputs. And the simplest approach is to just directly pre-process the data into some kind of fixed length vector with something using n-gram models, TF-IDF, or even regular expressions. So in a lot of custom domains, people will design custom regular expressions to extract the particular features they want in that kind of old school feature engineering machine learning. So the simplest sort of general purpose strategy for a long time had been n-grams. And the basic idea here is you take a block of text and you convert it to a set of columns where each column represents either a single word or a phrase. That's the n-gram. So each position in that vector then corresponds to that one word or that one specific set of words. And that in pre-processing your text, you determine the vocabulary, which is either the fixed number of words or the allowable phrases. And once that's done, anytime it encounters a word or a phrase it's never seen before, that can't be incorporated into the algorithm. Yeah, so the vocabulary is predetermined. So what this looks like, if I take a couple of like trivial examples, the sentence, the quick brown fox and how now brown cow, basically for a 1 gram, every one of those words, it gets introduced into the vocabulary. So the vector has 8 positions in it corresponding to each of the 8 words. And you'll see here that for each sentence, there's 4 1s and 4 0s because these 2 sentences are completely orthogonal. They don't share any words whatsoever. So that's the kind of the very minimal representation. There are variations on how you can do this. So that was a binary indicator representation. You could also count the number of appearances of the words. So in this instance, it wouldn't have made any difference. But if these were longer blocks of text, those words like the or a would appear multiple times. So bit of kind of NLP terminology, they're typically called stop words. You could actually remove all of those stop words before you do the conversion. That's a kind of a common approach that people take, but not always. And then there's approaches like TF-IDF, where the representation in that n-gram vector is more than just sort of the frequency. You do a calculation that takes into consideration factors across the whole data set. So the idea of TF-IDF is you want to, the sort of the key insight is that you want to consider how frequent the word or phrase is inside each individual text document, but you also want to consider how frequent it is across all of the text documents. Yeah. So intuition being, if it's frequent in this document, it's probably important, but if it's also frequent in all documents, maybe it's not so important because it's just a common word. So essentially it's a product of the frequency of the phrase inside the individual document, multiplied by the inverse frequency across all the documents in the corpus. So that's the kind of a modulating factor. Actually, let me pause for a moment. I should say, if anyone doesn't understand anything, I'm totally okay with you asking a question. I'll try and keep an eye on the screen here if you. Oh, Jose's doing it for me. Okay, awesome. Yeah, I'll just say that if I feel like the question's somewhat orthogonal to the actual flow of the talk, I might postpone it to the end if that's okay. But if something's not clear, please do sing out so that I can address it as it comes up. So that's the TF-IDF idea, extension of n-grams, where you want to consider both the frequency inside a given document, but also the frequency across all documents. Now, this is n-gram and TF-IDF was one of the most general purpose text processing techniques that was used for a very, very long time. And in fact, even in the kind of the recent AutoML products of the likes of sort of Data Robot, H2O, and the ones produced by many other of the competitors, TF-IDF was a common way to pre-process text in the suite of things that were tested. But there are reasons why we needed to move beyond it, and read kind of cases in which it doesn't work. But because the core intuition is just there has to be words or phrases, specific words or phrases that are important, and frequency of those words and phrases has to be relevant. And if those two conditions don't hold, then it's not a very good way to represent your text. So they're very, very poor at representing meaning in text because they don't understand anything of how words relate to each other. And they're very, very poor at capturing patterns across sequences of text, particularly when it relates to long-range linguistic structures. So as an example, if you were building a model that you wanted to predict the readability of a block of text, one of the key things that we know is that embedded clauses have a large impact on that. So an embedded clause is where you start a sentence, you want to add some additional information. So if you're writing, you'd put a comma, you add some additional information, another comma, and come back to your original theme. So that's an embedded clause, and you can actually do that multiple times, which is sort of quite common in languages like German. But we know that the more embedded clauses there are, the less readable a block of text is, but you can't represent that aspect of linguistic structure in an n-gram. So that's just one example of the kinds of structure and meaning semantics inside language that can't be represented this way. So how do we address these ideas of sort of meaning and structure? So one of the first kind of advancements that helped us get better at representing meaning was being able to represent words inside semantic spaces. So effectively what you want to be able to do is somehow represent a block of text so that these two example sentences, say for example, the dog jumped over the fence, the hound leapt across the barrier, in your vector space, they should be quite close to each other because their meaning is roughly the same, even though the words are different. And in fact, if you did it's worth noting that if you move the stop words and did an n-gram encoding, these would be completely orthogonal from each other. So there's in no way could the model learn that these have basically the same meaning. So how does that work? Before I sort of talk about that, I'm going to do a brief neural network primer, which is, I know everyone here, or I assume everyone here already knows what a neural network is. The thing I want to emphasize here is the importance of the hidden nodes. So in the history of neural networks, if you go back to sort of the McCulloch and Pitts models, they didn't have the hidden nodes. They only had 2 layers. And there was this period where these 2-layer networks are being experimented with, and then papers came out showing that it was extremely limited, the number of functions you could learn with them. And that was kind of, at one point was widely sort of retrospectively assumed to be the reason why that we went through one of these winters, AI winters, because people didn't know that you could do more with neural networks if you added these extra layers. So when they started adding the hidden layers in the middle, all of a sudden we got greater representational capacity, because all of a sudden now you could have, with the hidden layers, with the nonlinear activations, they were able to learn these representations, higher level representations of the input data, effectively learning features on the data. So the reason that's important is because that's what, when we start building models that learn semantic representations of text, we're exploiting this feature extraction ability of neural networks in the hidden layers. So probably the most famous model for this was the word-to-vec model that came out with a reasonably famous paper. And the basic idea here is you train the model to learn the relationship between a given target word and the context words, which are the words that precede it and follow it in a block of text. And there's 2 ways they do this, continuous bag of words and skipgram. And in both cases, after you train the model, you're going to be using the activation of those hidden layers as your semantic representation. Yeah, so we're basically exploiting this factor of how neural networks work to create a semantic representation of the text, and that's what we call a semantic embedding or a semantic representation. So what does that training look like? The continuous bag of words shown on the left is basically a model that predicts from target words from context words through to a target word, and the skipgram is the opposite. So from a target word, try and predict the context words. And so an example of what that looks like, if we had the sentence, the quick brown fox jumped over, our target word is brown. That's the word we want we want a representation of what the meaning is. And the first context word, presuming we've got a context window of 2 on either side, is the, also presuming we're not removing stop words. So basically in the continuous bag of words, we're trying to say, given you've got a sort of probability vector or effectively like a one-hot encoding vector of your vocabulary, the word the, can I predict that a common target word for that is brown? Or and in the skipgram model, you've got the input word is brown. You're trying to predict the context word of the. So you're doing that multiple times for all of the context and target words. And then once that process is done, you're able to extract that the hidden node activations as the semantic representation. The advantage of the skipgram model is that you only then need to use the model as it's originally developed. So you just feed in the target word and pull out the hidden nodes, whereas in some sense you have to kind of back propagate with the continuous bag of words. You have to set the output layer to your target word and then see what the hidden nodes that was hidden activation that could generate that, if that makes sense to everyone. So the amazing thing about this technique is that it really does appear to capture some idea of the meaning of words. So the famous example that was floating around at the time was you could take the semantic representation of the word king, subtract the semantic representation of the word man, add the semantic representation of the word woman, and you'd get something that was very similar to the semantic representation of the word queen. So it seemed the vector spaces that were learnt by these techniques seemed to have a kind of additive logic to them that represented a kind of intuitive notion of human meaning. And so what we would tend to do to use them in a machine learning technique is basically encode all of the words, add them up together so that by the addition of the semantic vectors, potentially normalizing them, but you'd still sort of create this vector in meaning space, and that was your input for the machine learning model. This technique worked very well in general, but it still had problems because by addition of the semantics of the individual words, you're still ignoring the order in which they appear. And so in this example here, if we took the two sentences, his writing is not good, and it is good he is not writing, they would effectively have the same meaning, you know, because most of the words in those sentences are the same. The word his and he are simply male pronouns. Writing, not good, and is are all there, and so the semantic vector through this additive logic would be basically the same, even though the actual semantics here should be the inverse of each other. So, core idea. We've now made a step towards representing meaning, but it still doesn't allow us to represent meaning of sentences. So rewinding a little bit, recurrent neural networks had been a technique that had been with us for quite a while as a way of dealing, a sort of independent way of dealing with these variable length inputs. But the core idea is you can process an arbitrary length sequence, be that text, be it a DNA sequence, be it a protein sequence, if you basically process it in chunks, and then as you process it, maintain a memory state of the previous activations you've seen. So the idea is you combat that variable length input by iteratively processing it, maintaining memory, so that when you've finished processing the sequence, you've got an internal representation of the whole sequence. So I'll do a visualization of how that works. Basically, you'll have on the left-hand side, the set of input nodes here it's kind of an abstraction. Imagine that is some set of numbers that represents the window you're processing. So it could be a representation of a single word or a single phrase. And then you pass that through to your input, to your hidden nodes. And then once that's flowed through the network, you then move to the next window frame inside the input sequence, and then when you pass that through to the hidden nodes, you also pass, the hidden nodes have layers that pass their previous activation back into themselves. So this recurrence over time allows you to sequentially process the sequence, all the time feeding the new input block with the previous activations of the hidden node, and those recurrent connections are what allow you to maintain a memory state of the the network. So independently, these things have been shown to have an amazing number of abilities. So there were early papers showing that they could use their hidden node activation space to create something like a stack. So they could do things like count by creating sort of a fractal space inside their hidden node layers that they could unwind if they needed to sort of count their way back out. Bunch of theoretical papers saying that they could learn to use that hidden node space for all kinds of different properties. But for our purposes, you can actually learn a sequential notion of the meaning of a block of text. So they're a very powerful technique, particularly when there's not long-range dependencies in the text, but they do still tend to have a few lingering issues. So they tend to emphasize the last part of the sequence. So if I go back to that previous slide, you can imagine if on the left-hand side, this thing here is a really, really long sequence, because there's this constant, the memory of the original, the first couple of input nodes depends on all these recurrent connections. It tends to get diluted over time. So recurrent networks tend to always emphasize the last part of the sequence. That was very hard for them to learn. So consequently, it was hard for them to learn long-range dependencies in the sequence. That's the reason for the LSTM, or long short-term memory network, the reason for its design. But it's also fair to say that it was not perfect at that. Like it wasn't perfectly able to learn any sort of arbitrary long-range dependency in the text. And that the fact that the whole thing had to be processed sequentially, because you've got these constant recurrent connections, made parallelization really, really hard. So it's computationally difficult to work with. However, they were still quite useful. So the original encoder-decoder architecture, which you've probably heard about because of transformers, but maybe don't know that it preceded transformers. It was originally a recurrent neural network architecture. And the basic idea was that you want to be able to, the task is, for machine translation, you need to take one sequence of text and convert it to another sequence of text. And this is the origins of the sequence-to-sequence model. So the core idea is we split the task into two subunits. The encoder is responsible for processing the input text, creating some kind of representation that can then be used by the decoder model that processes that and produces the output. So what does this look like in the original iteration? So basically, the encoder is a recurrent neural network like we went through before. You've processed your input text, at the end of which, using these recurrent connections, you've ended up with a semantic representation of the entire sequence. You pass that across as a semantic vector through to the decoder module, which is then going to do is a network that takes input from that semantic vector, but it also takes the current token that you're outputting. So initially, that's going to be a sort of special token called a start token, because you haven't produced anything. You feed that with the semantic vector into this decoder architecture and produce your first output, which in this case is DAO. And then in the next step, you then feed that first token through the decoder architecture, again maintaining the semantic vector in order to produce your next token. So sequentially maintaining the semantic vector, but always inputting what your last token was, and you keep doing this until you produce the end token. That's effectively the structure that was used to do the initial sort of sequence-to-sequence models. Now, it still had problems. So because we're using a sort of vanilla recurrent neural network in that encoder component, we're still washing out context from early on in the sequence. And so and that decoder module is still it's basically using the same semantic representation, and the only thing that changes every time is the input token that's the last token that was output by the decoder. So the attention mechanism was introduced specifically to solve these problems, and the way it was implemented, again, initially retained the recurrent neural network. So what you do is you process the input sequence as before using a recurrent network, sort of just leaving the recurrent networks connections off here for simplicity. But instead of keeping just the final activation of the hidden nodes, we're keeping all of the activations of the hidden nodes throughout the sequence. So now we've got the problem. We've now got an arbitrary length rather than an arbitrary length input sequence. We've now got an arbitrary length set of hidden node activations. So we need some way of dealing with that. The way we do that is the attention mechanism. So basically, the model now becomes, you take your initial token, start token, feed that into an attention mechanism, and then you iterate through all of your hidden node activations that you've generated from the encoder, and that will produce an attention value. So you'll note here that there's one attention value for every one of those hidden node activations. The intuition here is we're saying, this mechanism is saying, given that we just output the start token, how much attention should I pay to all of these hidden node activations that have been provided to me by the encoder architecture? You then take a weighted product of all of these, so multiply the hidden node activations by this attention value, and then that weighted product is what gets fed through the actual decoder network to produce your first token. You then repeat the process by feeding that first token into the attention mechanism. It is going to then generate new attention weights for all of your hidden node activations. You take a weighted sum of those, and that is what gets fed again through the decoder architecture. So the way we're solving, the kind of core idea here is we're solving the initial context washout problem by maintaining all of the hidden node activations through as the encoder produce the whole sequence. But then we're dealing with this variable length sequence of hidden node activations with the attention mechanism by learning this network that then learns how much attention do I pay to each of those given what I've just produced. Does that make sense to everyone? Yeah, lots of nods, which is good. Sorry, virtual people, I can't see nods, but I'm going to take the thumbs up. Awesome. Hi, question, yeah.
So does that mean for each token go through each set of values for through all of the previous ones? So you do the entire thing each time for each token.
Yeah.
And the attention value is per token.
Per token, yeah. Yeah, cool. Oh yeah, not going over here, yeah.
Yes, so can you explain how this relates to one of the things I understand about attention is that it knows, like for example, the chicken didn't cross the road because it was target.
Yeah.
How does attention solve for that?
Yeah, that's a good point. So so you're talking about like a pronoun resolution. So I guess the idea would be you've got it's important to remember this is sort of the initial implementations of attention. I think self-attention does a better job of that specifically. Because in this instance, one of the limitations of this approach is it's only considering the last token that it output. It has no memory of the previous tokens it output in the output sequence, if that makes sense. But it does have what it does have. It will know. It'll have the pronoun as well as the nouns in here in this encoding here. So it potentially knows whether to pay attention to the pronoun or the noun here based on the last token you've output. I realize that's a really poor answer to the question, but it's something like that. Yeah. Yeah. Yeah.
Alex, yeah, but hand raised. Not anymore.
Okay, I'll keep going. If you think of the question again or you want to type it to Jose, Alex, feel free. So that's adding attention to the encoder-decoder architecture. Yep, cool. Yeah, fire away.
Yeah, so just for clarification, we are looking at the past attention, the past weights, applying some attention vector on it, and then using that to generate the next one. And so we're kind of looking at like the nth last activations when doing the attention mechanism, right?
Yeah.
Okay.
Yeah. All right. So so this all leads up to self-attention and transformers. So for the reasons we're sort of talking about there, this works really, really well as there was a sort of a step change in machine-to-machine translation when this got introduced. But the transformer architecture, there's a couple of problems it's trying to solve. You still had recurrent networks in these original encoder decoders, which are computationally inefficient. You can't parallelize them, and they don't sort of some of the things you're talking about there, they don't have a perfect kind of sense of everything that's being produced in the output sequence. So in the attention is all you need paper, basically the idea is you want to do the same thing but without recurrent networks. And so you'll all have seen this illustration. It pops around the world. I'm not going to talk about all of it. I'm going to focus in just on the multi-headed attention component. Because other things like the positional encoding helps this thing deal with the sequential nature of it. But really, probably the thing that's most difficult, at least for me to understand, was how this multi-headed attention worked. Because a lot of the rest of this stuff is just sort of standard neural network blocks in one way or another. So what we're basically trying to do with this multi-headed attention, it's repetitions of a single self-attention block. And the idea of self-attention is basically you start with some sequence of word representations. I've got this sort of trivial example here of the bank of the river. So the colored blocks below it are kind of like an illustration of what that vector contains. And what we want to do is transform that encoding of the text into a new representation, one that is sort of sensitive to the full context and meaning of all of the text. So this example here, you might say the word bank might typically refer to a financial institution, but after a self-attention module, it's recognized that the presence of the word river in that sentence means we need to modify the way we represent the word bank because we now have better information about what it means. And this kind of goes to the kind of thing that you were referencing here, because we're going to modify any pronoun in this will be modified based on what are the actual nouns, proper nouns that appear in that sentence, so their semantic representation can be changed. Does that make sense? Yep, cool. So the key idea is we need the self-attention mechanism has these sub networks that produce three sort of values or three new vectors from every every token encoding. It's a query, key, and a value pair. And the way they work is, as say I'm trying to work out what my new representation of the word bank is, I'm going to take its query representation and I'm going to dot product it with all of the key values for all of the words in the sentence that I appear in. And then so I do that, I've now got attention weights, basically effectively saying the query key combination tells me for the word, if I'm the word bank, how much attention do I need to pay to the word the word bank, etc. So this is like it's like a personal vector of attention weights for the word bank. I then apply them by the value vector. So multiply the attention weights by the value vector that's been generated for every single one of those words, take a weighted sum of those, or take the sum of those, and that is my new representation of the word bank. Yeah, so those three, the query is the only one that's specific to bank in this case, saying because I care about bank, but I want to use the key to determine how much to pay attention to other words, the value to work out what my new representation should be, sum those up, and now I've got my new representation of the word bank. That's the kind of the core idea, the way that you can, yeah, fire away.
Trying to get similarity.
Yeah.
Why is it not symmetric? Why, if I'm looking for bank,
yeah,
versus you look at my bank,
yeah,
what's the kind of intuition?
yeah. So the idea. So I'll continue on with the pronoun example. If I'm the word it, which knows it's a pronoun, its query in some sense is going to be saying, oh, what I'm looking for is what are the nouns in this sentence that are most likely going to modify me? Because really the word it could be a stand-in for the word ball. Yeah, so actually my semantic representation should actually be the word ball because I'm just a placeholder for ball. Whereas the inverse is not true. If I'm the word ball, I don't want to be modified so that I'm represented now as a pronoun. Yeah, so depending on which word you are, it actually matters. That's why it's not symmetric. Yeah, far away. Oh yeah, so people couldn't hear that, yeah? I'll repeat the question. So it's a little bit backwards, so I can repeat the question after the answer. But the question was, why is it not symmetric? Why do we need the query key Why couldn't we just use the same vector to do that? And the answer I was giving was that because the relationships are not symmetric. So that basically, if you're the word it, you care about what the nouns are to change your representation, whereas the inverse does not hold. The word ball doesn't care so much that the word it appears in the sentence. It doesn't care in the same way. Does that make sense for everyone? Yeah, fire away.
So does that mean for any processing computation, you've got a set of tokens of size n, you need to do n by n processing,
Yes,
but you can parallelize
it can be parallelized. Yeah. So the question was, if you've got a set of n tokens, does that mean you need to do n by n processing? To which my answer was yes. You heard the rest. Fire away.
Is there an intuitive way to describe like this word attention? Like,
Yeah.
Does it mean what we think it means? Like when we think of attention, like how much importance do we assign to each word, given that I have this word?
Yeah.
Is that like full attention? Is that how we should interpret it?
Yeah, it's a little bit confusing. So the question was like, how do we interpret the usage of the word attention in this? Is it just like what we kind of independently think of attention? Actually, it's complicated because the word attention, depending on what discipline you've come through, it has different meanings. So psychologists have very, very specific meanings for it. But it just means, like you can think of it as either, what do you have to attend to? Well, actually, so the first idea is that the recognition that your input data contains internal relationships, correlations, and the way you think about every input part, what's important for it is different. Like the other parts of the input that it cares about is different. So basically what each component needs to pay attention to varies. So you have to learn that relationship of what to attend to. That's kind of the first part of it. And the second part is that machine learning can be improved by applying this because you can come up with better representations when everything is aware of everything else that's in the input. Yeah, another question.
So then how would you build the key query values for an input sequence? So would the model have to do one pre-pass, generate that for each based on its like training, and then
Yeah, so it's all back propagated. The whole so because I mean basically you'll get you know, once you've generated it, so say we're doing like sentence classification and you've got a new often so if you sort of go back to like old school NLP problems, like sort of even like sentiment classification, for example, so it's a binary class, maybe positive or negative, and you're only using this representation, often what people will do, there'll be a special N token, and you just take the N token representation as the thing you actually, it's sort of in the transformer nomenclature, they'll say you put a new head on it, which is to classify it, to do your classification. What will happen is it will backpropagate information about what was useful about that output vector you've taken, which will backpropagate through to, okay, which of these, you can see, okay, which of these values that the value dot producted with the attention gave me the most kind of error, which can backpropagate through to the query key combination that gave me that error. So you can, it seems convoluted, and I recognize for me as well, this is the hardest part to visualize how this whole thing gets backpropagated, but that's basically how it works.
I think the question was a bit towards the separation between training phase and production.
Oh, is that what it is?
kind of, yeah, like
So how the model exploits this relationship that you have built in training?
Do you mean like for like a fine tuning sense, or?
more that like, so you need for your input, say like set of tokens, query key and value weight for each of them, right?
Yeah.
And so if you're doing this processing, you can parallelize all these tokens. Oh, thank you.
Yeah.
So you need a query key and value weight for each token in the input set. And if you're processing them, you can parallelize the processing or the output value for each of the input values. But then where does the values for the query key and value numbers come from? Do you do one pass to generate all of those for each token and then one pass to generate the output value? Yeah, I think
good
that's
question. Yeah, cool. Awesome. So that's basically almost to the end. The summary is that basically self-attention now gives us this way to transform text into a contextually sensitive representation where every token is now has information about the rest of its context. There's other tricks they have in there, like there's a sort of like a positional encoding that maintains sequence information in it, so that you know the words, the order the words appeared in. All of the transformations can happen in parallel, and they're all influenced by other words in the text, and you can use it for more than just sequence to sequence. So as I sort of alluded to before, everyone probably knows here that the encoder decoder transformer, you can take just the encoder part and create BERT models that can be used for all of your kind of standard machine learning NLP tasks like sentence classification or sentiment analysis, etc. And then you can also use just the decoder component, which is what's given rise to sort of to LLMs, etc., where it's basically just learning how do you do next token prediction. So you can, the summary of what we've done here is we spoke initially about the problems of processing text and doing machine learning on text, how we essentially always have to deal with this, how do we get a fixed length vector that the machine can operate on. We spoke about simple feature vectors, either using regular expressions or the most generic technique that had been widely used for a long time of n-grams and TF-IDF. We then spoke about the problems that the ways that the issues of sort of semantics could be solved using sort of word2vec and these other semantic spaces, and then talking about recurrent networks and their ability to do this in a way that was was respecting the order in which words appeared, and how that led to the sequence to sequence model of one sequence to another sequence, and then how that model then led to the introduction of the attention mechanism as a way of making those sequence to sequence models better, which ultimately led to self-attention in networks and the current explosion in capability that we're seeing. That's the talk. So some credit where credit's due. I referenced a bunch of papers in there, which sort of, it seems somewhat weird given that at least half of them came from Google. So there was a bunch of other stuff that was really vital to me preparing this talk. Jay Almar's visual transformer posts, if you haven't seen them, are an amazing resource. He's very, very talented at communicating complex ideas sort of visually. The Rasa Whiteboard series on YouTube is also really useful. It talks about a whole bunch of NLP topics that's useful. And the Hugging Face Transformer book is also really good. It's got a great chapter on transformers, and then really practical chapters that are each focused on individual kind of NLP use cases and how you use transformers for them. And I think someone in the comments piped up something else they found really useful as well. So thank you. And I have a book out called Getting Data Science Done. It's not about technical stuff. It's more about how you do run data science projects and frame problems better, that kind of stuff. And I have on my GitHub IO, I have a bunch of kind of open source and research projects I'm working on. If I'm always looking for collaborators or people just to talk about them about if you're interested in any of that. Thanks for your time. Oh, any more questions? Yeah.
Thanks, John. Great talk. I know this was all about text, but how applicable do you think it would be for other problem domains? Like, for example, creating embeddings of behavior. Like, if you imagine a sequence of customer events as like a sentence,
yeah.
Could you create an embedding of that?
Yeah. So I know people are doing this. I know, I can't remember her name. There's someone who works in an ad tech company in New York who's doing exactly this kind of thing. She has representations of how people traverse the internet, particular behaviors that basically trying to sort of apply. They've got a custom, I think it's just an encoder model for that. Yeah, so it's certainly applicable. I think the consideration is, like, it has to be, first of all, is your problem one where it has to be a problem where you expect there to be attention makes sense, i.e. that other things in the sequence matter to individual sequences. So there has to be some kind of level of dependence between them. And sequence is probably also important as well. So even with the application of attention to images, sequence exists there, it exists in multiple dimensions. Yeah, so you can imagine even with 3D objects, you've got sequence in 3 dimensions as well.
Yeah, yes. I wonder if there's value in like hierarchical attention, like maybe at paragraph or sentence level, like are folks doing that?
I don't know. It's an interesting idea. Yeah, because you can. I'm not actually across. There's a bunch of recent papers about how you expand the length of context windows. So one of the limitations of the initial attention models was, you couldn't actually deal with arbitrary input text. So there has to be tricks for dealing with that. I mean, obviously you can run a BERT model over different blocks of text, then concatenate the semantic vector you get and then classify that. But then you're sort of getting into higher order sequence problems, because it could be that things that are said in one paragraph are actually reflecting on things said in the previous paragraph. So I don't know whether whether that's being solved hierarchically or not. With the long former and whatnot, maybe someone else in the talk knows, in the audience knows. But it's an awesome idea. Yep.
So in your talk, you make like a more and more complicated kind of solution that you can solve. Maybe I've missed it, but at what point can the model translate in between languages where the order of words is not preserved? Like you translate from English to Yoda?
Yeah.
Or something like that.
Yeah. So I believe that was actually shown, if you go back to, I'm pretty sure the paper, the Yoshua Bengio paper, this encoder-decoder plus attention. I'm not 100% sure, but I think this paper actually had an example of English to French where the order, like the noun phrase order, the subject, verb, predicate phrase, the order was flipped, something like that. And so they basically showed how, because the decoder component could see, it knows what it's just output. And because it generates the attention for this, there's nothing stopping it saying, like, I've got this kind of, the grading here is sort of like, you could say, pay more attention to this thing here, this thing at the end. There's nothing stopping it say, oh, because I'm a decoder for French, I know that once I've seen this thing, which is a noun, I need to pay more attention to this other part, because I'm going to be switching the order of words. So the attention mechanism allows you to arbitrarily switch order of words.
Cool. And another question, you having a broad experience across many industries, which are some business applications that kind of maybe surprising or not so, trivial, immediate?
Yeah. So I think it's fair to say everyone, well, a lot of people were caught by surprise as to how well these things worked. So I was surprised when I first started using, like, taking a BERT model that was pre-trained on a block of text and just finding how well it worked just almost out of the box, compared to, just doing sort of combination of bespoke feature engineering, TF-IDF and semantic representations. So I think all of the standard NLP kind of tasks work really, really well with transformers, at least with the encoder part I know, and I've sort of seen that myself. I'm less convinced yet by what you can do just with the decoder only component. Like, I don't know how the world's going to solve. I think the only thing that actually, I probably shouldn't comment on that. I don't know enough. I don't know enough about it, how that's actually going to play out.
Only you don't. If there are no more questions, I have plenty. What is your opinion about this idea that convolutional neural networks kind of are homologous to LSTMs?
Are there what? So,
homologous, that you can solve the same problem with any of the two, let's say, building blocks. I've seen that paper somewhere.
Yeah, I'm not sure. I'm not sure about that. I mean, to me, they seem to be solving very different. Like, so you think an LSTM is solving the problem of you can have a long range dependency across the sequence, and you don't know when that's going to, like, you don't know how far back the dependency is. So you need this internal memory structure that says, okay, maintain this state, and at some point I'm going to let that input that I've stored come out because it's going to be relevant across the range of the sequence. So long-term dependence. Whereas convolutional neural networks are sort of saying, well, actually, we want convolutions around specific regions within an image to capture these kind of rotationally invariant patterns. So it's more like rotationally invariant patterns that are in a local region in the convolutional neural network idea versus long-range dependencies that could be arbitrary length across, they could be anywhere across the sequence. So on the surface, they seem to be quite different ideas to me. So I'd be interested to know how they sort of demonstrate that formal equivalence, if that's what they're trying to do.
Yeah. Good, thank you. Any more questions?
If there are no more questions, so thank you very much, John, for a very informative talk. I really learned a lot and refreshed a lot of the concepts that I think, based on the interest of questions, it has been like a very well received talk for everyone. So we will make the video available in our webpage. Go